So let's go through the last few problems for section 4.4. All this stuff about using logarithmic properties. So we did a couple of these in class, but I'm just going to do them one more time, and then you can fast forward a little bit if you want to. So number 13, we're going to write each of these logarithms. We have a single logarithm, and we want to write them as a sum or difference. And we want to simplify as much as possible, and we don't want to have whatever's inside the log, we want that to be as simple as possible, preferably just one number or one letter, I guess, variable. So part A, log base 3 of 5z over w. This one is a quotient, but we also happen to have a product in the numerator, and so you might be comfortable applying both of those properties at the same time. So we're going to have log of 5 plus log of z minus log of w. So log, and they're all going to be base 3 of 5 plus log base 3 of z minus log base 3 of w. And so in a little bit, we're going to go backwards, and we're going to start with something like this, and we'll combine them back using these product and quotient properties. But here we go. So part B, this is a product, x squared times y. So we can start by writing this as natural log of x squared plus natural log of y. And natural log of y, that's as good as we can get, but the x squared, we can use the power rule to bring that 2 out front. So we can write this as 2 times the natural log of x plus the natural log of y, and then there we go. Okay, so part C was one that we didn't do in class. And so this one I'm going to maybe do a little slower. So we have natural log, and we have, to me, overall, I see a big fraction. So I'm going to apply the quotient rule first. So we have natural log of cube root of x squared. And you might want to go ahead and write cube root of x squared as x to the 2/3, but we'll do that in a second. And then minus natural log of the denominator, which is w plus z. So cube root of x squared is the same as x to the 2/3. The root goes in the denominator. The roots of a tree are at the bottom, so root goes in the bottom. So this is natural log of x to the 2/3. And then this natural log of w plus z, we can't do anything with that. It's so tempting to split it into 2 logs, almost like distributing that log, but that doesn't work, right? If it was w times z, then we would split it using the product rule, but that's not what we have. So it's just going to stay as is. There's nothing else we can do with this second natural log. But we are going to be able to do something with the first one. So, okay, this natural log of w plus z is just going to tag along and be part of our final answer. And the last thing we can do is use the power property to bring 2/3 out front. So 2/3 times the natural log of x, and then minus the natural log of w plus z. All right, and then this one we did do in class, and I'll go over it again. So similar to how we had a cube root up above, and that was the same as having 3 in the denominator. So this square root, we can write as all of this to the 1/2 power. So we have log base 2, and big parentheses, 4x over yz cubed. So nested parentheses here. This is all to the 1/2. But you could skip writing all this and just immediately write that this is going to be 1/2 times the log base 2 of 4x over yz cubed. Okay, so now we're going to do our quotient rule and our power rule. Our product rule. And this 1/2 is just going to kind of have to be distributed. And so what I'm going to do is just kind of put some big brackets or parentheses and then separate out this log with the product rule and quotient rule. And so I'm going to go a little slower than I did in class, but if you're comfortable with this one in class, just fast forward a bit. So log base 2 of 4x minus log base 2 of yz cubed. Okay, so that was the quotient property. So now each of these has a product, so we can use the product property. So we're going to end up with 4 logs inside these brackets. And this 1/2, we just keep writing it. So this is going to be log base 2 of 4 plus log base 2 of x. And now we have to be careful again with like parentheses or something. So either use some parentheses here after this minus sign, or just remember to distribute it. So minus log base 2 of y, and then so it would be, right, we would have plus log base 2 of z cubed, but you could go ahead and distribute the minus sign. So what we did in class was we just went straight to having each of the factors in the numerator is a positive log. Each of the factors in the denominator was a negative log. So, I mean, whatever makes sense to you is what you should do. Okay, so I'll just leave it like that. So now we've got equals 1/2. So log base 2 of 4, we can actually figure out what that is. 2 squared is 4, so this is just 2. And then plus log base 2 of x. And then I'm going to have minus log base 2 of y. And then minus, and let's go ahead and use the power rule for the z cubed and bring the 3 out. So minus 3 log base 2 of z. And it's perfectly fine to just leave your answer like this. If you wanted, you could distribute this 1/2. And so that would look like 1/2 times 2 would be 1. And then plus 1/2 log base 2 of x minus 1/2 log base 2 of y. And then minus 3/2 log base 2 of z. So either of these last two expressions, I would say, are simplified. All right, so here on this page, we spread out a log of something really complicated and got it so that all of our logs, whatever's inside, is as simple as we possibly could make it. So now we're going to do the opposite. And we're going to combine sums and differences of logs into a single one. So part A, it says log base 2 of z plus 4 times log base 2 of y. So the plus sign, you should be thinking product property, but before we can do that, we have to bring this 4 inside. The 4 kind of is a barrier to using that product property. So we're going to start with the power property and bring the 4 inside and write that we have log base 2 of z plus log base 2 of y to the 4th. And, if you want, you can use parentheses, but they are kind of optional. So now we can combine these into a single logarithm using the product property. So log base 2 of, and I would use parentheses now, zy to the 4th. And you could put y to the 4th times z, but all of that stuff multiplied together. And so notice we always have this log base 2. The 2 never changes. You don't add the bases or something weird. So then part B, we have some natural logs to combine together. And again, we do have this 3 that we need to bring inside. So natural log of x cubed, and then plus natural log of x minus 2. and then minus natural log. I'm going to do parentheses 5 just to kind of keep things kind of consistent. And so you can do this kind of 2 at a time, but we'll talk about how you could also get straight to your final answer from here. So natural log of, so we're going to do, for the first 2, I'm going to do the product rule because it's a plus. So x cubed times x minus 2. And I'm going to use parentheses, but you could go ahead and distribute, multiply that out if you wanted. And then we have minus the natural log of 5. So now the quotient rule says we're going to do a quotient. So the first argument, the first input over the second one. So we'll have natural log of x cubed times x minus 2 all over 5. And so there's several different ways you could write this, but one way you could distribute the x cubed inside, and so you'd have x to the 4th minus 2x cubed over 5. You could also write that 5 as a 1/5, or like out front 1/5 and then parentheses, or distribute it and have like 2 fractions. Anyway, several different ways you can write it. But notice that we have a single logarithm and everything is inside that logarithm. And so that should fulfill the requirements for Alex. And so you might notice the positive logs ended up, those arguments, those inputs ended up in the numerator. The negative log ended up in the denominator. Okay, so last thing we're going to do that's going to be on this test coming up is the change of base formula. And so this is finally how, if you have an older calculator, you can put any log in your calculator. So let's say you want to figure out what the log base 2 of 25 is. Well, 2 to the something, let's see, 2 to the first power is 2, 2 squared is 4, 2 cubed 8, 2 to the 4th is 16, 2 to the 5th is 32. Okay, so it would have to be 25 is in between 16 and 32. So this is going to be somewhere between 4 and 5. But to get a pretty, good idea of like a much better approximation than just between 4 and 5, we would like to be able to put this in our calculator. So what we do is use this change of base formula or change of base property. And so you pick whether you want to use natural logs or common logs. So natural log is the ln, right? Common log is the one that doesn't have the base and it's base 10. So just pick which one you want to use. I usually use ln because it's one less letter to write. Like, it really doesn't matter. And so you can write that log base 2 of 25 is equal to, it's exactly the same as taking the natural log of 25 divided by the natural log of 2. It's also exactly the same as taking the common log of 25 divided by the common log of 2. So the base of the log goes in the bottom when you do this change of base. And you're writing a ratio of logarithms here. And so whether you use the ln buttons or the log button, you're going to get the same thing. And I should have had this calculator already going. And I'm trying to remember how to derive this thing. It's not that difficult. I don't know if I want to do it on the fly. Okay, so log base 2 of 25 turns out is the same as natural log of 25 divided by natural log of 2. And notice how I'm closing off parentheses. This parentheses after your first log, that's really important to close off or you're going to get the wrong thing. Okay, so we said something between 4 and 5 a while ago, so 4.64, blah, 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 blah. And just by the way, you get the same value if you use the common log. Just make sure you're using the same kind, right, for both your numerator and denominator. And this calculator does have that log base where I can actually directly enter log base 2 of 25. So let's just confirm that that's going to give us the same thing. And it does. So let's say I wanted to graph log base 2 of x. Let's clear all this mess out. Log base 2 of x, so I could use, math menu if I have that, if I have this guy available, I could use that. But now, if I don't, I can still do it. So log base 2 of x is the same as taking, well, I'll just use natural log of x divided by natural log of 2. And so we could get into like how like every log is a vertical stretching or shrinking of every other log. But anyway, oh, I've got the window all goofy. And remember, whenever you graph a log, your calculator gives up and doesn't show you the full kind of asymptotic behavior as you get close to the vertical asymptote. Okay, so this says use the change of base formula and a calculator to approximate the logarithm to 4 decimal places. So if this is on your test, to show work, I just want you guys to show me what you're going to type into the calculator, whether or not you actually need to use the change of base formula. Maybe you have a newer calculator where you don't have to do it. You can type this in directly, but just tell me that this is the same as natural log of 15 over natural log of 7, or use common log, whatever. Just write that ratio down for me so I know that you know what the change of base formula is, because it is still kind of handy. Natural log of 15 divided by natural log of 7. Notice the base of the log goes in the bottom. And so 1.3917. 1.3917. And, 7 squared is 49. That's way bigger than 15, so it makes sense that it's something kind of close to 1. So then for log base 5 of 0.3, so again, I just pick ln because it's literally one less letter for me to have to write. Divided by natural log of 5. And so this is, we're probably going to get something negative. Like we probably would have to raise 5 to a negative exponent to get something around 0.3. So natural log of 0.3 divided by natural log of 5. And it is negative, so negative 0.7481. 0.7481. And so there we go. And I'll think about this guy. I'll see if I can remember how to derive this formula and maybe make you guys another video.